Hello everyone, thank you for joining this session. I'm Carlo Mazzocca from University of Bologna, and today I'll present you EVOKE. This is a joint work with Florida International University. So nowadays we all know that there are billions of IoT devices connected worldwide that generate an enormous amount of data. In this scenario, it's crucial to identify trustworthy devices in order to promote their collaboration and also to allow third-party organizations to use this data effectively. However, there are some challenges that are inherent of the property of IoT networks. So for example, IoT devices usually have limited storing and computing capabilities. There are frequent connectivity issues. Moreover, bandwidth constraints and low transmission range may negatively impact communication efficiency. Generally, digital identification methods falls into two categories that are centralized and decentralized. Centralized identity management system usually rely heavily on centralized entities, such as PKI certification authorities, and so they suffer from many issues, such as low scalability, single point of failure, latency, and network dependence. Given this consideration, digital identification methods that promote decentralization are more suitable to meet IoT requirements. So recently, the World Wide Web Consortium has standardized decentralized identifiers and verifiable credentials as two technologies holding the potential to efficiently implement the identity of things concept, providing each device with a unique identifier and enabling them to prove certain properties and capabilities. So a verifiable credentials is a digital credential containing a set of statements about an entity that can be cryptographically verified by any third party. An entity could be potentially whatever, including, as in this case, an IoT device. While similar to PKI certificates, verifiable credential VCs are much more, let's say, flexible because they allow proving authenticity over any type of data. They are issued by trusted entities that could be, for example, government agencies, let's say, and they are presented by a holder to verifier that can directly verify their authenticity and ownership, because within a verifiable credentials, there is a direct reference to the holder of the credential itself and to the issuer. So the verifier automatically directly retrieve the public keys from the verifiable data registry, and through asymmetric encryption verify both authenticity and ownership. So in the context of IoT networks, an issuer could be, for example, the manufacturer of the device that could attest some properties through a verifiable credentials. So for example, that the device is running a certain firmware version, or that the device is compliant with certain security standards. And on the other hand, the other device, let's say a verifier one, can decide to establish only trusted communication with devices that have met some security requirements or standards. So, of course, they are similar. VCs are similar to PKI certificates, so we may think about extending the revocation mechanisms that have been proposed for PKI certificates. However, there are some limitations that hinder their adoption, especially in IoT networks. For example, let's discuss them briefly. If we consider online certificate status protocol, a device presents its VCs to another one that has to query the issuer about the status. In this case, we have some problem because we have to assume a reliable network connection towards the issuer that could be difficult to guarantee, especially in IoT networks. And moreover, if we have many devices, all the devices will introduce a remarkable network overhead because they will have to send queries to the issuer. So other approaches are, for example, certificate revocation list, where the issuer periodically distributes a list of revoked credentials to devices. So when another device presents its own credential, the receiver has to check whether the credential is included or not within the list. So also in this case, we have some constraints that are represented by the fact that the amount of the size of the revocation list grows over time with the number of credentials that are revoked. For this reason, some alternatives have been proposed, for example, bitstring status list, where instead of having a list of revoked credentials, we have a bitstring, and we include within each verifiable credential an index referring to a specific position of the bitstring. So if the bit is set to 1, the credential is considered as revoked, otherwise it will be still valid. However, we always have the same problem that the size of this data structure grows with the number of credentials over time, and it also introduces remarkable network overhead. So to overcome this issue, we propose EVOKE. EVOKE is an efficient revocation mechanism for verifiable credentials in IoT networks. The key insight of our proposal is to employ a data structure that is independent for storing requirement and verification validity from the number of credentials in the network. EVOKE allows establishing trust with minimal computing and storing overhead, as each device is only required to store 1.5 kilobytes of data. And since the amount of data to share is very low, devices can also update each other with limited networking overhead. So we employed an elliptic curve cryptography accumulator. So the key property of the accumulator is that they allow accumulating multiple elements into a unique value whose size is constant and is known as accumulator value. So in our case, we accumulated valid verifiable credentials. And then for each valid verifiable credential, given the last valid value of the accumulator, we generate a witness. This witness is used as a proof of inclusion and is provided to each device. So basically, if a device has to prove its, let's say, authenticity and to have a valid verifiable credentials, it provides the other device with the credential, the corresponding witness, and the receiving device will combine this information to verify if their combination matches the accumulator value. If it does, the device is marked as trusted. However, since we are in a very dynamic environment, conditions may change over time, and credentials may get revoked because, for example, the device could stop working properly or may get compromised. So the issuer must update the accumulator value and recompute all the witness. So when the issuer shares this information, some device may immediately get the updated version of the accumulator and that of the witness, while some other may not immediately receive them, for example, due to networking issue or power save hibernation and so on. However, there is in EVOKE the possibility for an updated device to update an outdated one, because when they start interacting, they exchange their accumulator version that is also accompanied by a timestamp. So in this case, the outdated device can acknowledge being outdated and start disabling trusted communication. So in this way, it prevents that other devices may leverage an outdated version, this outdated version of the accumulator to be authenticated. So in EVOKE, there are two possibilities for a device to get update. One, if this device has enough networking capabilities, it can directly retrieve the updated version from a verifiable data registry. Otherwise, it will be updated by another device with adequate networking capabilities. And in this case, we'll talk about indirect retrieval. So we evaluated EVOKE in several settings. We started from commodity IoT devices. However, due to programmability constraints, we only consider devices that support browser connection. And as we can see, each device is required to store only 1.5 kilobytes of data for the accumulator value and the corresponding witness, while the time for verify validity is in the order of a few milliseconds. So to overcome the limits of programmability, we also consider hybrid networks. We consider a network, star network topology, combining commercial devices, IoT devices, and Raspberry Pis. So the Raspberry Pi acts as controller for the devices, and basically they implement EVOKE functionalities on the behalf of the device that they are controlling through their APIs. And we evaluated both latency for establishing mutual trust and end-to-end latency, that is the latency needed to transfer revocation information from one point to another one. We also compared EVOKE with a baseline that is the same network configuration, transferring a minimal amount of data without performing any operation. So just to verify which is the override introduced by EVOKE, that is in the order of few milliseconds, as we can see. And finally, as it would be impractical to evaluate EVOKE on thousands of millions of IoT devices, we conducted large-scale analysis. We simulated up to 1 million nodes with a revocation per day yearly of 10%. Each device interacts with 5 random devices within an hour, and we also accounted for different percentage of devices missing updates. As we can see, the most expensive operation in this case is represented by the witness generation that, however, as over time a high number of credentials get revoked, it also decreases over time. While as far as concern offline updates, as we can see also in the worst case, when 50% of devices are missing updates, we are able to update nearly the entire network. So to conclude, we propose EVOKE, an efficient revocation mechanism for verifiable credentials that require only minimal computing and storing overhead, as each device is only required to store 1.5 kilobytes of data. Our approach is high scalable, since it does not depend on the number of VCs for verification time and memory requirements. And as we have recently seen in the previous slide, it also allows to update a large portion of the network when many devices are missing updates. Thank you for your attention. If there are any questions, I would be glad to answer.